And in general, I can't promise it'll come back in a week. Vastly greater student in 2 weeks, but hopefully they'll do it typically in a week. We'd said we'd return them in recitation, but in fact, we may return them when they're available, right? I did post the homework solutions for homework 1. In fact, I meant to have posted it Monday. I sent it to the grader, but not the, didn't put it on the web. My mistake. So in general, I will get the homework solutions up quickly, and apologies that they didn't go up already. A couple of people have asked about supplementary instructor, tutoring, etc. And because of that, like I said, we lost our supplementary instructor at the beginning of the class. I don't know if we'll get a new one. I've renewed our effort to get one, but I can't promise anything. It's a little bit out of my hands. But if anyone feels the need for anything like that, please contact me. And we'll see. One solution is coming to see me. And to that end, I would like to, I'm just going to formalize and set up office hours. I think Professor Pete Kiernan also has office hours. I think they're posted. Is that correct? You guys know? I'm not sure. You have to look on the web. But I'll also open up office hours. Wednesdays after class, i.e. 4 to 5. And Thursdays, let me see, I want to avoid the time of the precepts, so I was thinking it's 10 a.m., but I can't remember when the precepts are. Is 10 a.m. before them? You guys do know when the precepts are, right? Not, huh? Provost hour. Precepts, wrong university. Some places recitations are called precepts. When, recitations, they're at 1:10, and do you want to do 11 then? You guys can vote. 11. We can do 11 or noon. 11. 11 it is. Okay? But as I said, you can come find me. I mean, you can find me in my lab, or you can send me an email, okay? I'll just make sure I'm in my lab on those times. I'll be in my lab mostly. So the default is 118 Rock. Although you should also search my office, possibly 202. But you probably aren't going to find me there. Okay? All right. I wanted to make one comment, which I should have made maybe already. It's a simple comment. It's simply that now that we've gotten to the point where we know that that's the total energy of a mass moving with some velocity, when I write this, of course, I'm implying that's gamma, what as we called it, gamma sub u. It's not to do with the transformation. It's just gamma associated with the motion of the particle. Similarly, the momentum is p gamma mu, either for the components or for the total vector, okay? There's one simple result of that. Since, of course, gamma is 1 over 1 minus u over c squared, square root, as u approaches c, as I mentioned in the very first day that we talked about relativity, as the velocity approaches c, this thing blows up, obviously. We've talked about that. So for instance, I plot the energy when the velocity is 0, the total energy of the particle. There's no kinetic energy, there's just mc squared. And then as we try to speed up, that happens, right? Also, and I mentioned this before, but just let me repeat, what is the kinetic energy? It is the energy minus mc squared. So that is gamma minus 1 mc squared. Certainly not a formula you probably thought you would see when you learned that kinetic energy was 1/2 mv squared, but that's the relativistic formula. It's not used that often, but it is used, and there it is. But back to my main point, if that's what the energy does, and similarly, this is what the momentum does, those things, of course, are exploding. And the point is then if I try to make a particle go the speed of light, there's all sorts of problems if I could actually get it there. But the main point is it would take infinite energy to get it there. All right? So the speed of light is truly a barrier. That really wasn't, until we did this energy and momentum case, the Lorentz transformations kind of got weird if I tried to think about something going the speed of light. But nonetheless, at least there wasn't a physical thing, but here it is, okay? You can't get to the speed of light if you have mass, because it would take infinite energy to get you there. And special relativity has been proven over and over and over and over again. All right, it seems very exotic, but for subatomic particles, it's easy to get them to the speed of light. The whole linear collider, which turned on this week, and we're still in day 3 of our extra life because we didn't die, proves that we know what we're doing. And the sad thing about this is that all the stuff you watch on the Sci-Fi Channel is just bunk, right? There are not going to be aliens coming here. Well, they maybe can, but they're not getting around this, right? So the nearest star is 4 light years away. If you could go, if we could get a spaceship that would power us up to nearly the speed of light, we could get there in 4 years. But, the nearest star that might have life like ours, hundreds of light years away probably, right? Et cetera. Space, there's not, as far as we can tell, there's just not going to be a way around this. There's not going to be this, warp drive. Yeah?
How do you have particles travel at a speed like that? That is created at that speed?
Very good question. Well, if I build up my formalism the way I have so far, I get to this point and something seems crazy. Then, of course, I told you, and in fact, your question was the exact thing I was going to say next. It was a great question. I had you derive that from these 2 equations, right? Hopefully there's some nice derivation sitting here, right? And this, I said, is very useful. Although we're kind of stopping in this course at the point where you would really start to use this a lot. But one of the places that it's useful is I have not built up a formalism for us to understand what I mean if there's no mass to a particle. However, this result, which in some sense I can consider just as profound and just as fundamental as these results, okay? In fact, it is even, and I can't justify this, but if you see this again at a higher level, you'll see that in some sense this is a more fundamental result. For m equals 0, E equals PC. Okay? And I was actually trying to think if there's an easy way to show you this from what I've done so far, and I'm not sure there is. But another result is if when you think about this, what you realize is that the U will be C always. Okay, but that's the main thing I wanted to show you. The energy is momentum times C. That's just, in other words, that's just this equation with m0 and just the E squared equals P squared C squared part. Okay? This is for light. And that's what it is. I don't try to go over here and ask some mathematical nicety about some limiting process where gamma is going to infinity and m is going to 0, and how does that all work out? Just forget that. Jump right to this equation, m equals 0. This is how light behaves. Let me mention one other thing, though. Neutrinos. When I took this class, when I first saw this stuff in the 1980s, we were said, oh, there's 2 particles with 0 mass. Photons, and we think one other particle. We weren't sure at the time. It's neutrinos. Neutrinos are these tiny ghostly particles, and we'll talk about them again at the end of the class, at the end of the year, but they're born in every nuclear reaction. So there's a huge number of neutrinos created all the time in the nuclear burning of the sun. They're created in all sorts of radioactive decay at a lower level, and they're created in nuclear reactors. And you can measure them. And it turns out they have a mass of 1 electron volt, or, well, m times c squared, of 1 electron volt, or less, actually less. It's a whole industry is figuring out, trying to measure that mass. The energy of an optical photon, as I mentioned earlier in the class, is 2 eV roughly. So if I give a neutrino as much energy as a typical photon, it is ultra-relativistic right then. And they're usually born in nuclear reactions where they have about an MeV of energy. So they're always flying around. They look just like light. They're going just about the speed of light. When I was in graduate school, a supernova went off. And a class of neutrino detectors had just turned on. And they actually saw, turns out when you have a supernova, almost all the energy comes out in terms of the neutrinos. Okay? Because they're so small, they can get out of the reaction, whereas all the other energy is kind of stuck. And this first signature of the supernova was in these neutrino detectors. They saw the supernova days before the light was seen. It was the supernova in our galaxy. That happens once, perhaps every few hundred years. We don't really know how often. It's only happened once in the last 100 or so years, and it happened in 1987. Anyway, and they measured the neutrinos, and they did timing, and they were able to see that the mass was really, really low. In other words, that the speed of light, the neutrinos were moving almost exactly the speed of light. Within errors, they couldn't tell that they had any mass to make it, velocity less than c. Okay? So this is the way you'll think about a zero mass particle. Any questions? Does that answer your assume that answers your question? Okay. So yeah, this is sad. There's going to be no traveling to another galaxy. Right? You know how close the center of our galaxy is in light years? Rough idea? Anyone would hazard a guess? No one would guess? It's about 10,000 light years, or a few thousand. The size of a galaxy is typically 10 to 20,000 light years. I believe we're out at around, 7,000 or 8,000 light years. Okay? Now it is interesting, if we built a really, really serious rocket and could actually accelerate to near the speed of light, one person can go do time travel. Can go do serious travel, right? If I got you boosted to a gamma of 1,000, which would require a fantastic amount of energy, okay? Just an absolutely fantastic amount of energy. Your MC squared times gamma times 1,000. Like I said, your MC squared converted into a bomb would, take out a part of Ohio, okay? So multiply that by 1,000. And then multiply the mass of the rocket, MC squared, times 1,000. If we could do that, essentially take a good chunk of the energy put out by the sun, for a year or say, put it all in one little rocket, send it, we might boost you up to a high gamma. If I boosted to a high gamma of 1,000 and sent you to the center of the galaxy, time dilation could mean that 1 year would pass while you went 1,000 light years. Okay? So I could get you a good ways to the center of the galaxy. Then you'd have to slow down. And the acceleration and the deceleration, we really can't handle, but suppose we magically could. You will have only aged a short time, and you could go visit another side. But everybody back at Earth would have utterly died, and when you turned around and came back, it'd be a few thousand years later. But you sure as heck aren't, popping 1,000 light years, and you age a little bit, and they age a little bit. It's just not happening. Let alone that the energetics are such that we're not going that fast. Okay. Now I want to talk a little bit more. I want to show you today some stuff that we're not really going to hold you responsible for in exams, but I think it's kind of a preview of what you'll learn later. I hope you find it worthwhile. Because you've heard about space-time, probably within relation to special relativity, and I want to talk about that. First, a little bit of formalism. Okay, so we have transformation equations, the Lorentz transformations. And at some point, you get tired of writing these, right? Okay? But let me massage them just a little bit. So that's v times t. Let me divide v by c and multiply t by c. And v over c is beta. Okay? And similarly here, what I'm going to do with this equation is multiply through by c and write that ct prime is gamma. Multiply by this by c, and it's just v over c, which is beta. Okay? And you notice now that I have a kind of symmetric relationship. These two equations are simple, but x prime and ct, sorry, x and ct have formed this kind of symmetric relationship. Gamma x minus beta ct, gamma minus beta x plus ct. Okay? And that calls out for a simplified way of writing this stuff. So let me take a small excursion. Do any of you know, have learned how to any amount of, just a little bit of linear algebra and matrix equations? A lot of you haven't? Okay. There's a way of doing things where if I make a matrix, where I say A, B, C, D, then that's going to somehow change a vector. Okay, so I have a vector x that has components x and y. So maybe I'll even say r. The vector r has components x and y. Okay, you are familiar with that, all right? What I can do is I'll multiply a times r. And what I mean by that is I write a, b, c, d, and I'm going to multiply this times x and y. And then there's just a simple rule for it. I multiply a times x and b times y, and I put them there. And then I multiply c times x and d times y, and I put them there. And that's a new vector, and I could say that's r prime. Okay? So if I had simply written down that r prime equals ax plus by, and that's the x part of r prime, and the y part of r prime was cx plus dy, which is messy, then instead, I can instead write r prime equals ar. And it's nice, and it's compact, and I have to write less. I still mean a lot. I mean this, what I just wrote that. Okay? And you're going to see this again and again and again. I know for a lot of you it's review. Well, this is exactly the situation we're in with x. X prime, I'm sorry, that's exactly the situation with Lorentz transformations. X prime has an x piece and a ct piece. Ct has an x piece and a ct piece. Okay? So, I'm going to erase all this. This was just your basics on how vectors work. And, matrix multiplication and vectors work. So again, this is just a shorthand, but it's quite useful. What I'll do is I'll create I'm going to call it capital X. And it's a vector that consists of x, y, z, and ct. Okay? And then, and of course, x prime, just, I put the primes down. So it's just like a normal vector. I wrote it this way. I could have written it as a column vector. I wrote it as a row vector. And I didn't put a vector sign over it because that's typically the vector sign I'm going to reserve for the space part. But I've added c times t. C times t has units of distance, right? And so I'm sort of equating c times t with distance now. I'm mixing up space and time. But the reason I do that is because Okay? This whole matrix is those equations. Gamma x plus 0y plus 0z minus beta ct times gamma. So it's gamma x minus beta ct. 0x, y, 0z, 0ct, y, same with z. And then minus, there's a gamma minus beta x, 0y, 0z, plus gamma, which I pull outside, ct. Okay? So magically. So all of this stuff, all of the Lorentz transformations, which were a big mess, if you will, are now replaced simply by this one equation, okay? Where A, well, as a matrix, it's a fairly simple matrix. It's symmetric. It's symmetric across the diagonal. It's got two diagonal elements, which are 1. It's got a lot of zeros. And it's just got gamma or minus gamma beta everywhere. Okay? How many people have seen this before? Just because you read ahead in the book or you had it in the class? Huh? Excuse me? Oh, okay. You had this with, okay, fine. Anyway, so that's the way to write this. And the Lorentz transformations now have been written very simply. Now, this analogy goes a little further. So I'm going to take what seems like a side detour, but then I'll come back. Let's ask an apparently unrelated, but in fact, similar question. Suppose I have just a simple two-dimensional xy. I'm going to do just simple, mechanics or something, and I consider a particle. It's got some value of x and some value of y. Okay? When we think about frames rotating, problems with rotational motion, it's useful to consider what happens if I rotate the coordinate system like that. So I have if you will, this is the S frame and this is the S prime frame. Now here I'm rotating S prime with respect to S, whereas in special relativity I'm translating. But in some sense it's a similar idea. This is the translation from one frame to another frame. Here's a simpler version of that. So I have an angle theta. And I ask, well, this point, if you will, was at x and y. But it's also got some values of x prime and y prime there, right? It has a value x and has a value y, but it also has a value x prime and y prime. What are x prime and y prime? I can get it by geometry. I'll do it quickly. This length, with that being theta and that being x, this length here is x cos theta. Okay? But it's not that. X prime is that piece plus that piece. What's this piece? If I take y here and translate it out, okay? And I take x prime and do like that, and I pull that down there, this length is y. Sorry, this length is y, and that length is y sine theta. And so x prime is x cosine theta plus y sine theta. Now I can go through and do a similar derivation here. That much is y cos theta. If I translate x up to here and draw another box, this bit is x sine theta. I know I'm going fast. You're going to see this again later. If you're not really following the details, don't worry. You're going to get this again later. Every time I sit down to do these triangles, I get confused for about 15 minutes before I finally straighten my head out. Okay? But my point was simply to show that if I had one system, and then I have a system that's rotated, I get a similar set of equations. X prime has a bit which depends on x, and a bit which depends on y, similarly here. And I can write that r prime equals cosine theta minus sine theta. No, that's a plus. Minus sine theta here, cosine theta times r. Okay, where by r I just mean xy, and by r prime I mean x prime, y prime. So this is the rotation matrix which transforms this point from being observed in one frame to being observed in a rotated frame. Okay? In some sense, I'm doing the exact same thing here. Yeah, okay, that just seems kind of mathematical. I just mathematically showed that both transformations can be written with a matrix equation. Okay? Well, let me take the analogy one step further. If you have a vector, and I'm going to observe it, not special relativity, just over here. If I have a vector, in other words, I have the distance. Oh, it's a very, very complicated drawing. Let me just redraw it. Here's the vector r out to a point x, y. Okay? If I look at this from any other frame, and in particular from this rotated frame, so I can consider this to be r in this frame, but it's some other, seems to have a smaller angle with the x-axis in the other frame, what is a constant? One thing that's obviously constant is simply the length of r squared. That's equal to r prime squared. And yeah?
Why is sine theta negative in the upper right hand corner?
No, sorry. I made a mistake. Thank you. The length is a constant. If you don't believe it, like we could square out this and square out that, and you know, this will be x squared cosine squared plus y squared sine squared theta, and a cross term 2xy cosine. I add that to this. This squared plus that squared, the cosine and sine squared are 1, the sine squared and the cosine squared are 1, and then there's a negative cross term. It's the same, it cancels. X squared plus y squared equals x prime squared plus y prime squared. A vector's length is preserved if I look at it when I rotate the frames. Okay? So far, so good? All right? Is there something similar going on here? Is there some preserved thing when I look at this so-called vector here that has x, y, z, and ct? And I'm sorry, I forgot to name this. This is called the 4 vector. You can sound impressive. You can talk about 4 vectors. Okay? Is there something preserved about a 4 vector when I look at it from one frame versus another frame? And remember, we're talking about Anna's frame versus Bob's frame. Okay? And the answer is yes, there is. It turns out the thing that's preserved, I'm going to call it x. I'm kind of inventing some notation here because I'm trying to make things simple and I don't want to write. You will see this written in different ways, okay? I'm not fully inventing it, but the book sort of uses this. This is in the last little bit of the book, by the way. Oh, and they used a different sign convention. It doesn't much matter. It's take the spatial part, the normal way you would think of taking the square of a vector. You know, you add in quadrature, the various components. But instead of quadrature adding ct squared, I subtract it. Okay? This is called the covariant length. Okay? It's the length of a 4 vector. It's just got this funny business. You take the space part, but you subtract the time part, squaring all the terms. Okay. Let me look at x prime squared explicitly. So remember, so x prime, it's little x prime, the vector, little y prime, z prime, ct prime, which is equal to, okay, x is gamma beta x minus ct, y prime is y, z prime is z for translation in the x direction only, and ct prime was gamma minus beta x plus t. Okay? That's in compact form. This is just what we've been writing. This is Lorentz transformations applied to x and ct. Let's square it. Yeah, I have a mistake. I flipped t and x. I just screwed that formula up. X minus beta ct. And I forgot my c here. I'm sorry about that. That's right. Isn't it? Okay. Let's go. Let me square this. Now, it's all, there's no longer, things in parentheses. It's all just squared out and added up. So let's square this and add it. It's gamma squared times x squared. There's a cross term, which is minus 2 beta ctx and a gamma, minus 2 gamma beta ctx. Then that gets squared, plus gamma squared, beta squared, ct squared. Okay? And then I add plus y squared plus z squared. And now I subtract this business. First, there's gamma squared beta squared x squared. Then there's the cross term, minus 2 beta gamma x ct. But there was an overall minus in the definition of my covariant length. And then there's finally this term. Again, it picks up a minus sign from the overall definition. This nasty cross term cancels. And let me just write it out more. I just need to do it. Bear with me, a little bit of algebra. Capital X prime squared, x squared times gamma squared minus gamma squared beta squared. Well, that's gamma squared times 1 minus beta squared. Plus y squared plus z squared. Okay, plus, there's terms that have ct squared in them. There's gamma squared beta squared, and there's minus gamma squared. So that's gamma squared times 1 minus beta squared. But of course, gamma squared times 1 minus beta squared is 1 over 1 minus beta squared times 1 minus beta squared is 1, right? Because gamma is 1 over the square root of 1 minus beta squared. So that was 1. That's a square. And that's 1. So this is just equal to x squared plus y squared plus z squared, the top line. And this was a minus sign. I am sorry. Let me make sure I got that right. It's minus ct squared with gamma order unity. And then I was adding plus gamma, so that's minus the minus. So all that was with the minus sign. Minus ct squared. Okay? Yeah?
Why is the first term on the bottom and the gamma squared, beta squared, x squared?
Mm-hmm.
Why isn't that positive for the same reason that the other sign switch?
Here?
No, a little bit.
Up a little bit?
No, down. Gamma squared, that term. Why isn't that positive?
No. So this here with a plus, a minus, and a plus is this thing squared? And then in the definition of how you create this length, you subtract the square of the time bit.
Oh, okay, the negative is squared.
So the negative times the whole thing. Okay? I know this is a lot of algebra, but at the end it's simple. Actually, the reason we're doing all this pain is because I'm getting results which actually are simpler and in fact easier to write. In fact, about the most tedious version of special relativity, but which is the one we teach you because it's straightforward and you work it up. But in terms of like algebra is if you just use the Lorentz transformations in a straightforward way. Because look what I've come to now. I have that when I create this 4 vector, x prime squared is equal to x squared. And philosophically, I really should think of this the same way as saying if I have a vector in normal space and I look at it from some rotated frame, the length has to be the same. Also, if I translate the frame, the length has to be the same. Okay? This is saying if Bob and Anna are going along and everything seems weird, if they look at the covariant length of their 4 vectors, they're going to agree on that. Okay? And a Lorentz transformation, in other words, moving from one frame to another involves rearranging the 4 vector according to the Lorentz transformation, which is represented by this simple matrix equation, and it will preserve this covariant length of the thing, of the 4 vector. So I know that's abstract. Let's try to make it a little more concrete. And actually, I understand on the homework that some people were getting tripped up just simply with the barn or the spaceport, problem and clocks. Okay? So let's apply this heavy-handed formalism to just look at Anna putting her, Anna flying by Bob's spaceport. Okay? Let's just look at that. And first we'll just practice the stuff that you had on your homework, your first homework set. So here's Bob's frame. Here's his spaceport. Here's Anna's rocket ship. It's in the S prime frame. Bob's in the S frame. Flying by with V. Anna has a length L Anna. Bob's spaceport has a length L Bob. Okay? Actually, I want a little more space to write. So I'll erase my nice equations. And let's look at this again. So first off, let's just do it the way we've done it before. We had a couple of results. The length of Anna's spaceship is bigger than the length of the spaceport, but we pick Anna to be going at a speed where, given the Lorentz transformation, it just fits, right? Anna's length that Anna measures is bigger than what Bob measures, or Bob measures Anna's length to be contracted by 1 over gamma. Now, let's just straightforwardly use the Lorentz transformations. Let me just write some things down here. Let's say that at x, and this you guys have to be good at, okay? Let's say that this is x1 at some time equals 0. I'll even call it t1. And then out here, x2 is the length that Bob measures. We'll consider Bob to be in one frame. Sort of at one time, all right? It was at one time in Bob's frame that Anna appeared to fit. We can define the time equals 0, x equals 0 condition in Anna's frame. So let's just line up the back of the spaceships. x1 prime equals 0 when t1 prime equals 0. I can just say that, right? No problem. x2 prime is L Anna. No problem. Okay? But time 2 prime is what? I have to use my Lorentz transformation. It's gamma times beta x, x2 plus ct2. So it's gamma. I'm sorry, and that's ct. I'm still now back in the other mode where I'm only thinking about t. So of course this is v over c squared, and that's just going to be t alone. So it's gamma, and there was a minus sign, v over c squared, x2, but x2 is just L Bob, okay? Plus this term times t2, but that's 0. That's it. That's the full analysis. And I could ask you questions different ways, one way or another, but again, you need to just be able to do that. The time is somewhere in the past that Bob was seeing the front of the ship fit in. Fine. Now, I said that x squared is measured the same for Bob and Anna. Sort of a corollary of it, which I'm just going to state, is that if I look at differences between two places, that's also an invariant. In other words, if I write some delta x squared, that's also delta x prime squared. And what do I mean by that? I mean for delta x, let's look at delta x1. We just form a vector out of delta x1, delta x2, etc. Dot, 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 right? Okay? That's also invariant. So let's look at this for Bob. I won't even call it Bob. We'll just, prime is Anna, unprimed is Bob. So for Bob, it's just, x is the spatial part. In fact, I have it written here. I should have just gone ahead and written it down. It's obviously just delta x1, delta y1, delta z1, not 1, delta x, delta y, delta z, delta ct, right? But when I square it, I square these and I subtract that. There's no change in y and z. Delta x in Bob's frame is x2 minus x1. So it's L Bob squared minus c delta t Bob squared. There's no delta t. That's it. Okay? In Anna's frame, what do I have? Delta x for Anna is L Anna minus c delta t for Anna. Delta t for Anna in Anna's frame is just this time minus 0. So it's minus c squared. And let me square all that. Gamma squared v squared over c fourth. Yeah, no, that's right. That's right. L Bob squared. Okay? And I say these two are equal. Let me go ahead and write that as Bob and Anna. I'll put the prime there. Okay? That's just to say L Bob squared equals L Anna squared minus c squared cancels that c fourth down to c squared, and then that's just beta squared. Okay? So that's minus L Bob squared times gamma squared beta squared. What I showed before, this is gamma squared minus 1. Okay? Okay, so then I have L Bob squared equals L Anna squared plus L Bob squared times gamma squared minus 1 with a minus sign there. Okay, so that's L Anna squared minus L Bob squared gamma squared plus L Bob squared. And this is L Bob squared. That cancels that. And I finally just have L Anna squared equals gamma squared L Bob squared, which I can take the square root of both sides. And then that's the result I would have predicted, or that's the result I started with. L Anna equals gamma L Bob. Okay? So it all relates. I'm just going to leave you with this. If we did more, if we worked further, you would see that, in fact, this really does turn out many times to be an easier way to work these problems, although it's not maybe so apparent yet. Let me finish with one thought today. There's sort of a related concept. I mean, you may well have heard that special relativity, time and space get warped or mixed together. That's the mixing. The 4-vector mixes time and space. So let me quickly, I only have a couple minutes, give you another way of looking at this. Suppose just for one-dimensional motion, okay, I have x here and ct here. Suppose I just stay put, but I consider 2 points at the same x, but one time and then a time later here. These two pair of points. These two pair of points, considering a vector which is the spatial part squared minus ct squared, there's no spatial change, but there is a change in time. It's just I sit here and then a little while later. So these 2 points are separated in some sense, what's called a time-like dimension. That's A. If I consider a pair of points like that, they have a space-like separation. That would be this point here and that point there at an instant in time. Now, a special case is if I have something where x equals ct. So case C is 2 points along this line. Well, what is x equals ct? That's the line, distance equals velocity times time. This is the line that light travels on. Okay? This is light-like. All of these are separations between 2 points. So if I just sit still, my 4-vector changes in the time-like dimension. If I consider 2 points at an instant in time, they're separated in a space-like dimension. It's this quantity space squared minus time squared, or ct squared, which is the constant, no matter if I look at it or someone else in a moving frame looks at it. Okay? But there's another aspect to this, which is I can either move this way or that way at the speed of light. Right now in this room, you guys have been doing exactly just this, and I've sort of been doing like this, okay? Obviously with tiny, tiny motion compared to how fast light can move, just considering one dimension laterally, just x here in the front of the board. But all of this, if this is the present time, I'll consider myself to be at t equals 0. These are all options available to me, assuming I could boost myself up to essentially the speed of light. I can't get over here. Even though the paper is only a foot away from me, there's never a way for me to get over to that paper faster than the speed of light. I can move over to the paper by going up to here, but I can't get to there right there. And then if I think of the past, at least in principle, it was possible that I occupied any of this space back here, but I couldn't have gotten out here. Okay? So this is called, and if I think of 3 dimensions, like y coming out of the board, this is clearly a cone. This is my future light cone. Or this is the cone is on the path that light takes. So the cone is called the future light cone, and I have to live inside of it. And this is the past light cone. No events out here can ever intersect me. There's no connection between points here or here and my present or my present, future, or past. These are acausal. This is an acausal region. It's a fairly simple argument I've made, but it's deceptively simple. It's just kind of restating stuff that's obvious, but in a way it's fairly profound, right? There's a possibility in the future that I can get to, and there's stuff I can't get to because I can't move faster than the speed of light. And a transformation from one frame to another can make things sort of shift within this cone, okay? I mean, at the limit, if I consider a frame which is moving at the speed of light, I can shift something from on this cone here to there. Or more realistically, I'll shift things a bit. I can't transform, I can't access this space. Delta x squared would be imaginary over here, okay? But delta x squared, we're going to agree on the length, but 2 different frames disagree on how much of it is along the time dimension and how much is along the space dimension. So finally, to conclude, you can think of the Lorentz transformations, you can think of this change in special relativity as sort of a rotation in time-space, a warping in time-space. You mix time and space, and the amount that time and space are mixed is different for these 2 frames that are moving at different velocities. So I'll leave it at that, and we'll finish up relativity quickly on Monday and then move on.